Hello, my name is Pedro and I'm here to present our work entitled Development of a Small-Scale Testing Machine for Use with Interferometric Monitoring Methods. I'm going to start with a brief introduction, then I'm going to talk about electronic speckle pattern interferometry, our main monitoring method, namely regarding its working principle and our 3D setup. Afterwards, I'm going to highlight a few details regarding the machine's mechanical design, as well as the control system design. I'm going to finish off with a few conclusions. Material testing procedures are increasingly using image-based methods for strain field measurements, with extensive use of digital image correlation in particular. There is interest in extending this use to other image-based interferometric methods with increased resolution, such as electronic speckle pattern interferometry, or ESPI, which is a very high resolution interferometric method that is commonly used for displacement measurements. However, the measurement of displacement with optical methods at such high resolution is usually limited by assembly and vibration issues. In particular, ESPI requires very stable conditions, therefore it should be mounted on an optical table inside a dark chamber, which may have limited available volume. Therefore, the goal of this work is to develop a testing machine for these optical methods, for assembling in edges optical tables while fitting the dark chamber, reaching a maximum load of 20 kN and a velocity of 240 mm per minute. As I previously mentioned, ESPI is an interferometric full-field method that can be used for displacement measurement with very high resolution, around the 20th of the laser wavelength is common. Our 3D ESPI setup uses 5 different beams, all created from the same laser source, to generate 2 in-plane and 1 out-of-plane ESPI setups, which allows us to perform X, Y, and Z measurements independently. 2 of those 5 beams pass through a mirror and piezo assembly, which is used to produce control phase maps to acquire images that will feed the carry method to create phase maps. To measure displacement in the X direction, we use 2 beams on both sides of the camera, aligned with the measurement axis. The U displacement can be obtained from the phase measurement, the wavelength, and the angle between the camera and the beams. To measure in the Y direction, we also use 2 beams, now along that axis, applying the same type of expression. In our setup, the out-of-plane part uses an object beam from the X direction, the one with phase stepping, and a reference beam shining directly onto the camera. Therefore, the Z sensitivity is not perfectly aligned with the camera, but it can be corrected by knowing the X displacement. Our 3D ESPI system is shown in the picture. You can see the main components here, namely the beam sources for the X direction, the Y direction, and the Z direction, which reuses one for the X direction ones. We have also the fiber couplers that separate the laser into the different beams, the shutters, which allows us to select which one to use and are controlled with a custom device, and finally the phase stepping mirrors, which are controlled by 2 piezo controllers by Thorlabs. Regarding the mechanical design of the machine, using the mentioned speed and force requirements, we were able to select a motor, a QBL 4208 from Trinamic, as well as the necessary gearbox and coupler. We added a wire sensor for redundancy in position measurement, as well as mounting end stops in the moving beam's path for safety. The main goal here was to use empty specimens with our ESPI setup, therefore one of the main concerns was the alignment of the crack with the center of the ESPI's measurement area. Finally, we added a load cell, a height adjustment part, and optical table fixations. Regarding the control system, and the electronic circuit in particular, the central part is the motor driver, a brushless motor driver that is also from Trinamic. It is powered by a AC/DC power supply. We have a few safety features as well, such as an emergency button and a power relay. This relay is controlled by a custom end-stop controller, which is constantly monitoring the end-stops and the PC output to ensure proper operation. This PC output is performed by a DAC from Measurement Computing, which is also responsible for acquiring the position data from a wire sensor and acquiring the force data from a load cell, which is amplified by a commercial strain gauge amplifier. The timing of the main control loop is defined by a high-precision timer. It starts by reading the force and position values using the DAC, then the motor parameters such as torque and motor position. If it is in force control mode, it then implements the PID control loop. Afterwards, it performs a check of the user-defined virtual boundaries, which are independent of the end stops I've mentioned earlier, and if it fails, it will stop the motor. Finally, it will record data, if enabled, followed by triggering a graphical user interface update. It should be noted that other control types are not part of this loop, as they are already integrated in the driver. The graphical user interface uses one main window. We have three charts, one for the measured force, other for the motor torque, and the last one for the position. A list of the current values of force, torque, and absolute and relative positions, as well as the motor's position. A live force displacement chart. On the bottom left we have the action commands, and on the right we have the data record button, the 0 buttons for position and for the load cell, and finally a settings button, where we can set force and position limits, as well as other settings. This machine is already being used with middle tension specimens. Here we have an example where we analyze the behavior of the specimen from 1750 to 2000 Newton. We only used the y direction, and we were able to obtain good quality phase measurements, as well as the respective displacement fields. To conclude, a custom portable testing machine was developed for use with interferometric optical methods, in this case ESPI. It is capable of reaching a maximum load of 20 kilonewtons and a maximum speed of 240 mm per minute as designed. The ESPI results obtained with the machine are promising, showing good quality phase maps and displacement fields, and the machine is already operational, being used in multiple projects and with different specimens. Thank you, and if you have any questions, feel free to ask.